My name is Natalie Urson, and today I'm going to be going over the third lab of the semester, which is my group title, Determining the Kinetic Friction Coefficient of an iOLab Device on a Wooden Laminate Surface. So for this lab, we were finding the coefficient of friction between the felt pads on the iOLab device and the laminated wooden surface that it was being pulled across. And we chose to use the accelerometer and the force sensor in order to collect data to investigate. So for the force sensor, it measures the strength applied to the iOLab in newtons, whereas the accelerometer measures the acceleration in meters per second squared of the iOLab in the x, y, and z directions. However, we only actually recorded the data in the acceleration in the y direction, which was the direction that the iOLab, it was the axis along which the iOLab was moving, to avoid error due to measurement of the gravity in the z direction. And so for our setup, we had the iOLab on the desk, and we attached a string to the force sensor. We started pulling it along at roughly a constant velocity, and then started recording data as it was already moving. The iOLab weighed 200 grams, and because the y direction along which the iOLab was being pulled was the negative y direction, we had to take the absolute value of the force readings for our data calculations here. And you can see here on our free body diagrams, we are assuming that the force is positive as it is pulling to the right. So that's just something to note for later. So for our redesign, we actually added weight. So we added a 14.9 gram soda can, see here. And we had the same setup, ran 3 trials again, and collected that data. So we assumed that gravity was constant, the surface was consistent, and then that the weight of the can increased the normal force present. So since we actually started our trials while the can was, the iOLab and the can, or just the iOLab, were already moving, there wasn't a specific part of the graph where it was static versus kinetic friction. And that lab design was approved by the TA. So there's nothing specific to note, but here's a couple examples of graphs that we used to pull our data from. We got the average force in newtons and the average acceleration in meters per second squared of each of the trials. Experiment 1, trial 3 was a bit of an outlier, so we took that out just to increase the accuracy of the average, which is part of the reason why we did multiple trials in the first place. So for our calculations, we used the sum of the force equals mass times acceleration, and then we pulled the mass of the iOLab, and here in green, you can see the addition of the mass of the soda can in order to calculate what the frictional force was. And you can see here that we use the force minus the friction because those were the only 2 forces acting in what the iOLab has down as the y direction. And then we plugged in that frictional force to the equation. The friction equals the normal force times the friction coefficient for kinetic friction here to solve for the kinetic friction coefficient. And then we average those together for the trials to get the 2 you see here for the initial design versus our redesigned experiment. The coefficient of static friction is greater than that of kinetic friction because its corresponding frictional force is larger. When an object is at rest, there's more contact with another surface, and there's technically some bonding going on at a molecular level. And once that object is moving, those intermolecular forces are reduced, decreasing friction. So that makes sense. And then for our redesign, the reason why we added weight was essentially to increase the normal force present. And since, again, using the sum of the forces equals ma, you can tell that the normal force is equal to the force of gravity. So for these 2 diagrams, you can see that the force of gravity will be larger on the redesign due to this 14.9 gram soda can. So having a higher normal force increases the accuracy of when you calculate a kinetic friction coefficient because it decreases the impact of any observational error of the force, and therefore the friction, again, sum of the forces equal to ma, by the iOLab. So for our redesigned experiment, we got that the average kinetic friction coefficient was 0.2169, which is about the same, slightly less than that for our initial experiment, which was 0.2515. Which makes sense because in theory, those coefficients of kinetic friction should be the same regardless of the normal force and mass because it is the same 2 surfaces in contact with each other. And while they are very similar, we can assume that the redesigned experiment coefficient is actually closer to the true value just because that normal force is larger. And again, it would increase the accuracy. There are some limitations to our experiment. We did do multiple trials in order to increase the accuracy. However, we only used 2 of the trial data for the initial design. And we did remove the outliers, as I said. Pulling the iOLab at a perfectly constant speed is a bit difficult. An average acceleration was relied on for the calculations, as I mentioned. And the weight of the can might have been exactly in the middle of the iOLab, which could have had a little bit of an effect. The temperature of the testing environment can cause coefficient changes, but should have been consistent between the 2 designs. iOLab might have been perfectly calibrated or maintained perfectly between the trials, which could have caused potential error.